Okay, so in the next 3 lectures, I'm going to go over some examples of deriving the electric field due to a number of different charge distributions. And we're going to start off with a line charge again, but this time it's going to be a line of charge bent into a quarter circle, like so. Okay, with a total charge Q total on it, and let's say the radius of the circle is R. And let's say it's positively charged, and I want to calculate the electric field at the center of the circle. Okay, so let's go through the procedure that I outlined. So firstly, define the charge density, right? What is the charge density here? Well, it's a line charge, so my charge density lambda is going to be lambda, the charge per unit length, which is total charge over the length of this wire. Well, the length of a complete circle is 2 pi r, the circumference of the circle. This is a quarter of that, which is pi r divided by 2. Okay, and the divided by 2 is on the bottom, so we can bring the 2 up top. Okay, so that's the charge density defined. Next, define the point to calculate the field at. Well, that's this point here. And what we want to do, by the way, when we define the point to calculate the field at, I should add here that we should, at this point, we should make a quick sketch of the field vector to get an idea of what direction it's pointing in. So what direction is it going to point in at this point here, due to this charge here? Well, if you imagine a little piece of charge up here, and if we only consider this piece of charge, that's directly above this point, so the field due to that piece of charge will be pointing directly down. The field due to this piece of charge here, if we just consider this piece of charge directly to the left of this point here, the field due to that is going to point to the right. And by symmetry, we can keep finding pairs of charges like this, and they're all going to give vectors that by symmetry add up to point in the direction 45 degrees below the horizontal. So by symmetry, we can say that the electric field points down and to the right. Okay, define our coordinates. Now, I'm going to tell you a little trick here, and a word of advice. It's always tempting to just blindly define x and y coordinates the way we always do. Okay, we've got x. You might define x pointing this way and y pointing this way. Okay. Well, in that case, our electric field is going to have an x component and a y component. So you're going to have to find 2 components of the electric field, add those components together to get the total field. And the thing is, if we are smart, we can avoid doing all of that work. Okay. How do we avoid there being 2 different components to this electric field? The way you avoid it is you choose one of the axes to point in the direction of the electric field, which means the 0 component along the other axis. Okay. So in other words, a smart choice of coordinates would be, let's use a different color for this, would be to point our x-axis along the field vector and our y-axis perpendicular to the field vector. Now, all I have to do is calculate the x component, and that is all of the field. There's no y component. So I save myself a lot of time doing that. Okay. And our choice of coordinates is entirely up to us. That is, it doesn't affect the physics of the situation. In real life, there are not x and y axes following us all around, right? They are just man-made things that are, that we come up with to solve particular problems. Well, it also is going to help if we define our axes this way. It actually helps us. It's going to help us to rotate this whole situation, to view it so that the x-axis points horizontal, okay, like this. So I'm going to redraw it that way. So here's the point here. We've got our field vector here, and this is our x-axis here. Okay, this distance is the radius r of the circle. Okay, so we have defined our coordinates. We now need to, the next step is to divide the object up into infinitesimally small chunks and write down the charge on any one chunk dq. Okay, so we're going to divide it up into what we're going to pretend are very small chunks, because I can't draw them as very small chunks. And each chunk has a charge dq. So how much charge is on one of these chunks? So what we need to do is we need to find what the length is, dl, on one of those chunks. And at this point, it's useful to define the angle subtended at this point here by this little arc of length dl. Let's call this angle d phi, say. And this chunk is at an angle phi relative to the x-axis. So this is the angle phi. Right. By the way, you see why you need to draw big pictures increasingly, right? This is not small, but it's not half a page, which I require you to draw pictures at. And it's getting a bit squashed. It's getting harder to see what's going on because it's so small. So this is why I try and make you draw pictures as big as possible. Okay, so dq by definition is lambda dl. Okay, now dl we can write in terms of this angle d phi there, because the length of an arc of a circle is just equal to the radius of the circle times the angle subtended by that circle. Okay, then we can write down the little piece of field at this point here. It's just going to be dE. By the way, this is number 5 on our checklist. Write down the electric field at the chosen point due to the charge dq. So dE, this bit of field here, again, this is why you need a bigger diagram, is equal to k dq divided by the distance between here and this chunk of charge here. Let me highlight it so we can always recognize which chunk of charge we're dealing with. So that electric field is equal to that. We want to calculate the total electric field E, which points to the right, and we want to use symmetry to simplify that calculation. Well, there are going to be there's always going to be another chunk of charge the same distance below the x-axis as this is above the x-axis, contributing a field with the same x component but opposite y components. So the contribution to the x component of the electric field due to that charge is dE cosine of phi, and we can write this as k dq is lambda r d phi, so lambda big R d phi times cosine of phi divided by big R squared, right? And this r cancels one of those r's. So we're left with k lambda over r times cosine of phi d phi. Okay, so this is the x component due to this. The y components are all going to cancel because we know that the overall electric field points in the x direction. So the magnitude of the total field is just going to be what we get by adding up all of the contributions to the field of each tiny chunk, right? So each contribution is given by this. We need to add them all up. because they are infinitesimally small charges, adding up means doing the integral. Okay, and the integral goes from phi is down here, this is 45 degrees, which is minus pi divided by 4, up to plus 45 degrees, which is plus pi divided by 4. So k, lambda, and r are all constant. The radius of the circle doesn't change, for example. So all we're doing is the integral of cosine phi d phi. And we can, that's a fairly easy integral to do. Cosine phi integrates to sine of phi, evaluated between minus pi over 4 and pi over 4. Okay. Well, sine of phi evaluated at pi over 4, what is that? That's sine of 45 degrees. That's 1 divided by the square root of 2. And this gets added to, or you subtract sine of phi at minus pi over 4. So it's minus 1 over the square root of 2. Which equals 2k lambda over r times the square root, or divided by the square root of 2. 2 divided by square root of 2 is square root of 2 times k lambda over r. Note that this is only valid at the center of this circle. Let me just rewrite this equation here. This is only valid at the center of the circle, okay? So it's not valid if we are at a different distance than r. So we can't, in this case, do the important step of going a long way away from it, or getting very close to it, right? Because this formula is only valid under those circumstances. So always check to make sure that it makes sense to ask what happens when you go a long way or closer to the charge distribution. 9 times out of 10 you can and should do this, but make sure that it makes sense to do so.